So if you want to find correlation with the calculator, I would say the easiest way is to use linreg, which you will find in StatCalc. You do not need to make a scatter plot. You do not need to find z-scores. The calculator will do all the calculations necessary for you, which is pretty sweet. All that you need is to have two variables in your stat editor. I often use L1 and L2, but you could use different lists. What some of you may need to do first is turn diagnostic on. If you do not have diagnostic on, then the calculator will not show you R when you do linreg. So I will show you how to do that now. You only need to do this once unless your calculator gets reset. Okay? So to find diagnostic on, go to the catalog, which is second zero. Second zero. And a shortcut to the D's is by pressing the matrix button because it has a D above it. That saves you some time. By the way, the catalog contains all the calculator's functions. And you can use these when making programs. Diagnostic on is the one that you want. Enter. Enter again. Now, please go to Stat, Calc. You can use number 4 or you can use number 8. They basically do the same thing. The only difference is that for number 4, the slope of the best fit line is called A, and for number 8, the slope of the best fit line is called B. It's the only difference. I will use 4. It stands for linear regression. We'll talk later what that means. The calculator must be told what your x variable is, or where it's located, where your y variable is located. We're not using a frequency list here. We don't have like a list of frequencies stored somewhere. You can have it store the regression equation in a y variable, but I'm not going to use that. Then calculate. If you're on the old OS, then you won't see this stat wizard. Not a problem. You don't even have to specify L1 and L2. You can leave those blank and the calculator will assume L1 and L2. You can explicitly state the list, though, by using the second button and one of the keypad numbers, 1 through 6. And then to separate X list and Y list, you use a comma, which can be found above the 7 key. So calculate. And there it is. Negative 0.82 about. And that's what we got when we did the more elaborate method with finding the z-scores and the z-score products and adding up the z-score products and dividing by 1 less than the sample size. Okay. Any questions on finding R with the calculator? Very handy. Sir? The A value is the slope. B value is the y-intercept. R squared is the square of the correlation coefficient. We'll talk about that in Chapter 8. For now, all we need is the last one. If you did not have diagnostic on, then the calculator would not have shown you R or R squared. Other questions? So you'll want to be able to guess these correlations, like I said, within 0.15 hopefully, or at least within 0.25, okay? This one here, I would guess around 0.7, maybe to 0.8. It's positive, so it's going to have a positive correlation. It looks linear, and correlation measures the strength and direction of a linear relationship. And there's not too much scatter about a line of best fit. But there is some. So that's what a 0.71 correlation looks like. So moderate, positive. Next one, you have more scatter about a line of best fit. And it's a flatter overall type thing. And the flatter it is, the lower the correlation. And by the way, this 2 means that there are 2 values at that spot. So positive, but more scatter about a line. So this is a moderate relationship. And I probably would have guessed this at 0.5 or 0.6. So this is what a 0.46 correlation looks like. This one here it's easier to guess them when they are close to a line. So it would be negative 1.0 if all the points were collinear. And we're pretty close to a perfect line there. So that's what a negative 0.99 correlation looks like. That's very rare to see. Next one. Notice the effects of the cluster. It's all about a line of best fit. If you were to draw a line of best fit through, you would have to include that cluster. Or maybe have to is not the best word to use. Okay? This point here would have an influence. It would make the line closer to horizontal a bit. And it would make the correlation closer to 0. So it should be accounted for. However, it's 1 point versus 3. So notice the effect of this outlying cluster here on making the correlation appear stronger in an absolute value sense than you might have thought it should be. And if you were to remove those points there, then my expectation is that the line would look more like this, more horizontal, and thus the correlation would be closer to 0. Next one, this one's pretty easy. Very strong, positive. The points are very close to a line, so that's what a positive 0.99 looks like. This one, notice the effects of the outlier. This point here, and I did the calculation for you. If you take the outlier out, the correlation becomes weaker, or expresses a weaker relationship. You're getting closer to 0. Again, draw a line of best fit and use that to make a conclusion. But that's what a negative 0.47 looks like if you have an outlier that follows the trend there. Please note, the Pearson statistic only measures the strength and direction of a linear relationship between 2 quantitative variables. It is inappropriate to use it for a nonlinear relationship. So as you can see here, we have a perfect quadratic relationship or association. But the Pearson statistic is 0. So if you didn't look at the scatter plot, I think you would be very much misled. This one, I heard from a lot of people that they did not see the outlier. Outliers matter quite a bit. Without the outlier, this would have been a 1.0 correlation because all the points are collinear and they're not horizontal. Anthony asked a question yesterday about a horizontal relationship that actually doesn't have a correlation. It's undefined, but that's very rare. If you have some type of slope, you will get a 1.0 or negative 1.0. This point here, because it is so far deviating from the trend, take a look at the scale here. It's maybe 45 points away from this value here. This will exert a lot of influence or a lot of leverage. Again, think of drawing a line of best fit that included this point. It would be relatively flat. We'll talk in Chapter 8 about what makes the line of best fit the line of best fit. But this point here certainly is going to exert influence on correlation and on the line of best fit slope. For something like this, this seems to be an error. If it was an error, then I think everyone can agree remove it, report the calculation without it. If we couldn't find a good reason to remove it, then I would leave it in and calculate the correlation with and without it and report both of them. Here's another one where we're seeing the influence of a single point. Without this, the correlation is 0.13, which was very close to the guess of 0.1. And yeah, just looking at these points here, it's positive but weak. So I can understand that guess. This value here exerts a lot of influence on the correlation. It's going to make it appear stronger. As you can see, the actual is 0.7. Last one, look at the effects of clusters. They have a dramatic effect. If you look at each of these clusters separately, which is something that I would do, you would get correlations close to 0 probably. But overall, this has a correlation of 0.95, and it's related to the slope of the best fit line. The College Board would be in agreement with me if they gave you a question like this, for example on a free response. They would expect that you would say that the clusters should be separated and 2 separate analyses should be conducted with 2 separate correlations calculated. And I encountered a free response that involved univariate data recently from the College Board, in which they gave a histogram like this, and they said, what's the problem with reporting a single measure of center? And the answer they were looking for was there are 2 distinct clusters, so providing a center for both is misleading. It doesn't represent the whole very well, and it seems more prudent to calculate 2 separate centers to separate the distributions, which I can understand. As a former engineer, if I saw this, that would be very unusual, 99 times out of 100. And I would go into the data and try to understand why do I have the 2 distinct clusters, what's making this group different from this group, and I would most likely separate the 2 and redo the analysis. Okay, so like I said, that was the first pass. Any questions on what I went over?